Conservation Conference. This session is being recorded, so just so that you know, you may have seen that pop up. A little housekeeping here, just first as we get rolling here with our first presenter. You have the option to have on subtitles if you want. So if you want the words on the bottom of your screen as the presenter is talking, some of you may already see that if that setting is set for you. Otherwise, down at the bottom of your Zoom screen, you may see the option, the three little dots for more options there, and you can click on that if you want to add that option onto your, to see that for your presentations today. So we are excited to get started with this first session here. We are in the Educational Theory and Practices track, and our presenter is Dr. David Harwood, and he's at the Department of Earth and Atmospheric Sciences at the University of Nebraska-Lincoln. And he is going to be talking a little bit about climate data and some interesting information today with us. So I will turn it over to Dr. David Harwood.
Yeah, good morning, everybody. I'm happy to be here to share some information with you about climate change and about how I communicate climate change to my students and to the public when I teach this. And hopefully you'll be able to pull away some concepts, maybe anchor some things you already understand, but maybe find some other ways to approach this important topic. So a couple of running themes are going to be going through this presentation. One is just a sense of hot and cold. And this image behind us is kind of a cartoon of what Antarctica, where I work as a climate scientist, looked like in the past, sometimes being very cold, sometimes hot and vegetated, and the questions of what drives the Earth's cycles to provide warmth or cooling. So Antarctica is a cold, frigid iceberg or ice cube, or whether it's a green, lush with life kind of environment. And my screen's not advancing. Here, just a second. It's odd. Very, very odd. Hold on a second. Yeah, so, why climate change? It's in the news. It's affecting our lives. We have a really, really warm winter this season. And every 4 or 5 years, all the scientists get together, policymakers get together, and they meet to talk about and review all the literature we understand about climate change. About a year ago, the IPCC's assessment report number 6 came out, and several things were changed in there. One indicated clearly that it is human derived, and the language of the IPCC also changed a bit in using expressions like unequivocal or high confidence or extremely likely. I mean, scientists are pretty conservative in how we present things. We want to make sure we understand it before we present out there, and the language has changed on this issue. We know a lot about this. In many ways, we are negligent if we don't act on it in a big way. And of course, we watch the news, we see hurricanes, frequency and intensity increasing, irregular weather, global fires, drought. All those things are manifestations of the fact that we are changing the planet. This presentation is about communication of climate change, and I want to draw your attention to a group at Yale University, of the Climate Connections Group, that is very much focused on communicating climate. And one aspect that they presented was this concept of 6 Americas, that there are dismissive population or doubtful population, all the way to concerned and alarmed parts of our population. And of course, we interact with a variety of people as teachers and students from different political and social backgrounds and things, and they fall within these different categories. And the purpose of this 6 Americas is kind of to let folks know and understand that, know your audience, know who you're talking to. And if you're presenting some things about climate change, perhaps say the same thing 3 or 4 different times with a different message for these different audiences that we're working with. So I wear a lot of different hats. I am a scientist. I'm an Antarctic scientist, a climate scientist, as a professor in doing research in the Antarctic realm, trying to figure out what has happened in the past. And by understanding the past, we're better able to predict the future. As a father and a grandfather, I am very concerned about where we are headed in the future in terms of our environment and our climate. but I'm happy to share this information and perspectives that I've gained over the course of my career as a communicator, but also as a scientist about these issues. And my theater or venue for communicating a lot of this to students at the University of Nebraska is through a course I focus on Antarctic geosciences. So many of the things I'm going to be presenting to you today are derived from different programs and different data sets that I use in my classroom. But of course, I have a semester to do this, and here we've got 30 minutes or so. So this is something that we are all engaged with and should be engaged with. We are approaching this situation where it's too late to make some changes. Some things may be irreversible. Some people say climate's always been changing, and it has. We have a really clear understanding about what natural scale, timing, and size of climate change is. And we can clearly say that it's never been as fast as it is now. We can look at long data sets. Each one of these columns is a decade from 1850 up, and we can track this in terms of a average temperature, let's say over that time period. And we can see that in the last several decades, things are much, much warmer than they have been in the past. And these are not things you need to believe. These are empirical things that are measured. We can plot carbon dioxide concentrations, as we've been seeing over the last century or so, compared to temperature variation from the atmosphere or from the ocean, and we can see that there's this relationship. Temperature and CO2 are connected, and we'll see that some more. Some people have a interesting perspective about what is climate and what is weather. And I think by breaking this down in terms of scale of things that we experience as individuals, your students experience, by looking in terms of space here from a centimeter up to continent scale things to the whole planet, or in terms of time, right? This would be one day, going down into smaller and smaller time scales and up into longer and longer time scales. But we can plot those phenomena that are considered weather or climate across this, and we can clearly see a separation here between things that are weather and things that are climate. I often ask my students then to think about their experiences, their personal experiences with hot and with cold, and in thinking about patterns and cycles, right? And in thinking about space and time. Are there things that students experience regularly that are cyclical in terms of hot and cold? And of course, eventually through some discussion, they come up saying, well, yeah, day and night, right? And that is controlled by a pattern of the Earth and its relationship and angle to the sun. As it revolves around the sun and rotates, we get different daily patterns. Seasonally as well. The Earth's revolution here gives us things on a longer time scale. And with that comment there, is this predictable? Yeah, you could say it's like clockwork. Indeed, it's so predictable that we set our time to it in terms of natural scales of hot and cold. Are there any aspects that deal with the Earth's environment and longer scale things that also are predictable and work in kind of a clockwork way? And we'll work through that. Indeed, there are very many things that we can predict. I'll often give this chart out often on the first day of class or second day of class to get them to start looking at some data. And what you're seeing plotted through here is carbon dioxide, and that's kind of in the yellow record here coming from ice cores, and then measured directly from the atmosphere. And we can see it's climbing. And this is projection into the future of where we may head with increase in carbon dioxide in the future. But then we also have plotted on here is the temperature record, and there's a lot more variable as weather can be, but it's also showing a similar trend. Again, seeing that climate and CO2 and temperature are married, they're linked together, showing similar kinds of trends. And I also focus on this first line here in the box. 1896, Svante Arrhenius, he predicted based on physics of the atmosphere, physics of the greenhouse effect, et cetera, that if we double CO2, the Earth is going to warm by 5 degrees. And I have them make a projection and see if that prediction was right. But a point to make in this is that climate science is not new. It's not something that is new. The politics associated with climate science is new, but we've understood an awful lot for a very long time. And of course, you can break up these patterns into different periods, but overall things are accelerating and increasing as we go forward. are there longer scale patterns of hot and cold that we can look at? And indeed there are. We'll walk through some of these. But one pattern of cold here, 20,000 years ago, as we know, there are large ice sheets that covered the northern part of North America, large ice sheets that covered Scandinavia, northern parts of Europe and Siberia, and was this a one-time event, or has it happened repeatedly? And we have a really good record to know that this is also a cyclical event. It has happened repeatedly and regularly with similar types of timing and pacing as we can predict with daily variation, yearly variation. There are some longer scale patterns in this. Right, well, so how might this work? If we have all of this ice trapped on land, it has taken moisture out of the atmosphere through evaporation and precipitation, storing that water on the continents, which has led to a low stand of sea level. And the shoreline back 20,000 years ago, when those ice sheets were there, was out here. You can see the width of Florida Peninsula is actually almost doubled out to this point. As those ice sheets in the northern hemisphere melted, sea level rose, and it rose progressively across this continental shelf to where it is presently. I asked my students what this other shoreline in this image might be, and that would be the shoreline if all of the ice on the planet were to melt. So sea level and the coastline is not a fixed feature of our planet. It depends on where we are in the climate cycle and how much ice is on the planet. It's something that's variable. And what I want to walk you through right now is to see how these variation in climate and in ice sheet history can have a regular, understandable pattern. How are parts of the Earth's spheres, the Earth's systems connected? What are the feedbacks that control some of this natural climate cycle? So I'm going to walk you through something here that's going to be talking about linking the ocean, linking the lithosphere, linking the biosphere, and linking the hydrosphere, and all together in this as well with the lithosphere. And of course, Antarctica has this large ice sheet still on it. It has an equivalent of about 60 meters of sea level if it were to melt, or 180 feet. The scale of the northern hemisphere ice sheets, these are at the same scale, would have covered all of this area, would have covered this area as well, was about twice the volume of the present Antarctic ice sheet. And this went away 20,000 years ago, only 20,000 years ago. That's not so very long. When we think about Antarctica and its potential to raise sea level, the West Antarctic ice sheet, which is more directly coupled to ocean heat because it's grounded below sea level, has an equivalent of maybe 5 to 6 meters of sea level potential of rise. Greenland about the same amount. Antarctica being a lot higher and colder has other potential to raise sea level. I want to talk about some of the things that control this and what are the drivers behind whether the Earth is hot or cold on different timescales. And taking a look at the Earth's atmosphere is an important sense. Here we have the troposphere and the stratosphere and going on out. And just to talk about the role of the atmosphere in terms of heat coming from the sun. And when some people talk about the greenhouse effect, they have a misconception that it's actually the greenhouse gases are trapping the Earth's or the sun's radiation coming into the Earth and warming things up. And that's not true. It's actually another step involved with that. The sun actually comes through the atmosphere, through those greenhouse gases, because it's coming in as light, as shortwave radiation. And it makes its way through the atmosphere very directly. But when it hits the Earth's surface warms. And it's then the heat, the infrared radiation, long wave radiation that's coming off of the Earth. It's the heat that then gets trapped by the greenhouse gases. So it's not really sunlight, but it's heat from that sunlight that's radiating off the Earth that gets trapped. And the thicker the blanket of CO2 and other greenhouse gases, just like on a cold winter night, the thicker the blankets you have on, the warmer things stay. So it's somewhat analogous to this scenario of sunlight can make its way through your windshield in your car. It can warm your dashboard, can warm your seats. The heat from those surfaces that are warmed by the light, that heat can't get out if your windows are rolled up. And as Svante Arrhenius understood from 1896, it's the physics of these molecules where that actually drives how much of that heat is absorbed. So I also take my students on a project looking at some data from a tower in Wisconsin that has sampled the air at various elevations up on this tower. Here you can see that long tower, and sampling the air at this level, this level, this level as you go on up has revealed some interesting properties there. This is 1 week in July, and we see that carbon dioxide levels here, 560 or so, increases and decreases every day, increases and decreases. I ask them what's controlling that. And of course, a lot of folks have a view that it has to be humans, it must be rush hour or something like that. But then I go back to this cycle and say, yeah, but look, what color do you see there, right? It's all green, so it's photosynthesis. And we look at the timing of all this, right? During when it's sunny out, the biosphere is extremely able to, capable of pulling carbon dioxide down to kind of a base level. When sun goes down, respiration kicks in, carbon dioxide's given off, right, at these different levels. Some other patterns in looking at this data set, they can see that there's kind of an asymmetry here, that the lower level level sampling responds first, the higher level ones respond a little bit later, and that's clear on these 3 cycles. In these other days through here, the pattern shows some similarities, but it doesn't show the same variability. I ask them to try to think about what that might mean, and maybe it's a cloudier day, a sunnier day, however that makes a change, or in this case where there's no vertical change, everything's all together, probably a really, really windy day, and some students actually go online and look at historical bats of weather to figure out what was going on with Wisconsin. But the point to raise with this is that the biosphere is really capable of changing carbon dioxide levels, right? Other folks have gone and looked at longer term records of carbon dioxide to see if there are some patterns of change. Mauna Loa Observatory, middle of the Pacific Ocean, great place to look at this. This gentleman, Keeling, started this the year I was born, 1958, and he noticed that there is an annual cycle of increase of carbon dioxide and decrease. So just like the daily cycle we just looked at, Earth responds also to its seasonal changes. We can see that pattern through here, but there's this long-term trend and increase as well. Again, empirical evidence of just measuring these things. This site right here is pretty interesting and pretty helpful from Scripps. It takes us to the Keeling Curve data that are here, and you can look at that long-term record. You can look at 1 week's variation, you can look at 1 month, you can look at 6 months, a year, you can see this pattern developing. And then you can also look at how things have changed, from like 1700 or 10,000 years. We can actually see how much this was stable until more recently as it has just shot up. And then we can get this longer term record, which I'm going to build for you here to see that our current CO2 levels are so much higher than what we've seen for almost the last million years of time here. So there are these other different patterns and different trends that we see here: short-term trend, long-term trend, and the pattern of breaking this up. So we have a pretty good record of how CO2 has changed from 1958 to the present day. But considering space, where might you go if you wanted to see and understand whether this is consistent on other parts of the planet? Get my students to think about that, and they say, well, put some other sampling stations elsewhere. You've got Wisconsin, you've got Mauna Loa, right? So they end up saying, well, folks, go to the South Pole, another place where there's not a lot of influence from human activity. There's a clean air facility that the US has put at South Pole Station to sample and measure that, and it's the same trend, right? So it's kind of validation that there is a annual cycle through here of variability, but there's also a steady increase in this pattern. In considering time through this, where might we go if we wanted to see beyond that 1958 sampling, go back in time to see what we could understand? How might we do that? Think about that for a little bit and then go and see what scientists have done. Scientists have actually gone to drill ice cores from the tops of the Antarctic ice sheet, tops of the West Antarctic ice sheet as well. And then collecting samples of ice going deeper and deeper and deeper and older and older and older into the ice sheet. It is a great archive of past climate conditions on the planet and also past atmospheric conditions. So as snow falls on the surface of Antarctica, it gets compacted, it gets compressed, it gets buried, and eventually it traps ice. What scientists do is they'll take samples of this ice and they'll stick it in a vacuum chamber suck out all of the air, and then melt the ice. And any gas given off from the bubbles in the melted ice is a sampling of the ancient atmosphere. So we have a really good record of past atmospheric change. Again, going from snowfall down to coarse granulated ice. When we're drilling down through this solid ice through here, it's trapping bubbles in through there. Two projects that have really revolutionized how we look at the Earth climate over almost the last million years. One was from the Epica Ice Core, which we can see the facility here. And you can see this has taken, several years to drill down this deep, 3 kilometers into the ice sheet to collect that ice core record. And here you see the scientists in here, and they're, I'm sure, celebrating reaching 1,000 meters, 2,000 meters, 3,000 meters in terms of getting this this ice core record. So this would be the plot of the ice core gases measured from the surface of the ice sheet here. This would be today, and going back in steps of 100,000 years. And by melting that ice, scientists noted that carbon dioxide levels dropped to about 180 parts per million. They kept drilling, measuring those samples, and it came back to about 280 parts per million. They kept drilling, going back in time. It went down again, went up again, down again. And this is a pretty consistent pattern. By using that ice, you can also melt the ice and measure the different mass of the isotopes of oxygen, oxygen 16 and oxygen 18, and the mass of hydrogen, hydrogen deuterium, to be able to interpret temperature, because there's a fractionation based on temperature from these, which we can then interpret. And you'll note from temperature of the ice when it was formed in these ice cores, it follows a similar pattern to CO2. You plot them on top of each other, and it is the same pattern. So again, reinforcing that there is a direct relationship between greenhouse gases like carbon dioxide, methane, and others, and temperature. And they drive each other. It's not that one is driving and leading the other, but they are a positive feedback on each other to control some of these changes. The Epica ice core drilling went back even farther than the first drill hole, the Vostok. It goes back almost to 800,000 years now. And you can see that there's a steady pattern of glacial, interglacial cycles of increase and decrease in carbon dioxide, of the temperature pattern, and it's also matching there with methane. From that one figure, the first figure I show on the first day of class, I asked my students to plot what that data set would look like in through here in this field. And they get confused, because the scale is a bit different. That was, 150 years or so. And here now the width of that is just 2,500 years. So indeed, it's a vertical line, which gives them, I think, a bit of a shock to note. It's a bit of a trick question, but that the rate of change is so fast. It's unprecedented for the last million years, the rate of change of this carbon dioxide increase. I now want to play a video for you here of that's going to walk us through a pattern of change and see how these curves are developed. What we're going to see here is all the different stations where, like Wisconsin Tower, South Pole, Mauna Loa, where carbon dioxide has been monitored. And we're going to track progressively year after year after year the increase and decrease in carbon dioxide at South Pole and at Mauna Loa. And over here, we're going to see from the North Pole across the equator to the South Pole, and we're going to see these values kind of going. It's called a pump handle because the Northern Hemisphere, which has a lot more variability, seems to actually drive the increase in the South Pole record. But let's play this and see how it comes up. Hopefully there's not an advertisement here. Yep, I have my students.
This is the world's first reusable cotton swab. It removes up to 5 times more excess earwax.
I have my students raise their hand whenever they reach their birthday. So the dark circles up here are reflecting those stations that are not influenced by human activity, right, or any kind of urban changes. Those that are gray are more variable and volatile, as you'll see over here as well. They're showing more variability. But overall, there's a pretty consistent pattern as we walk forward in time towards today. You'll also note that the North Pole and the South Pole here, they're showing inverse sine waves here because there's not a lot of vegetation in the Southern Hemisphere. And just like our seasons, right, those two are going to be respiring or photosynthesizing in different periods, different seasons as you go through. And as we walk closer to today, we can see it's a pretty steady pattern. And this is predictable, right? It's actually accelerating a little bit, also by the amount of carbon dioxide that we're putting into the atmosphere. Yep, these things are just proceeding here along pretty steadily. But then we get to the point where we can start to get to 2019, but then start to go a little bit farther back in time. And the way we can go through this by not just looking at the Mauna Loa and the South Pole records, but we can start to go back in time looking just at the Mauna Loa record. And that pattern continues. And then scientists drilled a hole off the coast of Antarctica here and got a really high resolution record of the bubbles in the ice from the edge of Antarctica. And that's what you're going to see plotted through here. Right, so we can clearly see that change from 1880 industrial revolution up to today, and then start drilling. Now we move into the Vostok ice core record, which I just walked through, of drilling deeper and deeper in time, and we can see that CO2 levels drop down to 180. They increase as we go back in time, increase up to about 280, basically where they were pre-industrial. And there's this pattern and cycle through here. We now add the Epica ice core record onto this, and we go back farther in time. So there is this steady, little bit of random through here, but there's kind of a predictable record of this climate variability in terms of CO2 change. Of course, this leads us to considering what causes these changes in CO2, what's natural, what's not natural. And we can think about the carbon cycle through here, from volcanic emissions of carbon dioxide, from all of the carbon that's stored in limestone, coal, oil, and gas in the biosphere, et cetera. And then we start to think about the feedbacks here, as I mentioned before, about the lithosphere, the hydrosphere, the cryosphere, and the biosphere all playing a role. I want to walk you through that. So again, these different shorelines. Under the scenario when we had large ice sheets on the covering North America, here's the coastline. This is all exposed land, rivers draining off across here, and removing ocean sediments and delivering the carbon that was in these sediments back to the ocean. When that carbon is eroded, dumped into the ocean, oxidizes, it adds more carbon into the Earth's system, adds more carbon dioxide. The Earth starts to warm by the greenhouse effect. The ice sheets start to melt, sea level starts to rise up to this point. But then we get to the point where the continental shelf here is flooded, it's covered. Estuaries like Chesapeake Bay and Delaware Bay are capturing organic muck, dark, stinky black ooze, and that is pulling carbon dioxide out of the Earth's system. It's burying it and sequestering it here. What happens when sea levels high like this and you start to put a whole lot of carbon into the continental shelf and into those estuaries? Carbon dioxide is removed from the Earth's system, the active Earth system. CO2 decreases, the globe cools, ice sheets form. So we get this natural level of variability that's driving the pattern of change. And that's why the variability stays within that box that we see in the ice core records. If we think about some other potential variation, other variability, not just in terms of the margins of North America, for example, or other coastlines, but if West Antarctica, for example, which is vulnerable to collapse, and all of the organic productivity in the ocean around it, if that increases and covers across West Antarctica, we can think about feedbacks here as well. Burying of a lot of carbon across West Antarctica, what's that going to do to the Earth system? That's actually going to be a regulating factor as well, causing a feedback that would drive the ice sheets to expand again. So that's kind of a control. But there's some other patterns that we don't have a lot of understanding of or control of, like melting of permafrost, release of methane and CO2 that's in those areas, all operating potentially at different times. But some points I want to raise here is that carbon dioxide and CO2 and temperature, they're married in this pattern. And also the pattern of CO2 and temperature, it's staying within this box, right? And that's because of these natural feedbacks I just talked about, of how the lithosphere, the biosphere, the hydrosphere, and cryosphere all work together. There also are some other patterns that we can see in terms of the timing of this record. Every step here is about 100,000 years. Just like the Earth's revolution, the Earth's rotation, giving us daily or seasonal cycle, there is a pattern and cyclical change in terms of ice volume on this that's going about every 40,000 years, every 100,000 years. And just like the other orbital patterns, this is being driven by changes in the shape of the Earth's orbit, being more elliptical to being more circular, changes in the tilt of the Earth's axis, which also varies, gives us our 40,000 year, and some other factors. So it is like clockwork, even on longer scales, right? We can understand what's controlling some of those. Is the variability from the orbits, is that sufficient to drive these ice ages and grow ice sheets and make those changes? No, it's not. But it gives us the pacing, it gives us the timing, it gives us the ability, gives the Earth the ability for its biospheres to interact and impact and amplify these changes, right? So the biosphere, the carbon cycle, the greenhouse gases, all those things I was just talking about can amplify the pulse that's coming from these orbital changes. Some of the themes that we have for today, what's natural and what's not natural. What are the patterns of change? These are things you can get your students to do. By reading the past, how does that help us or guide us to predict the future? If something's happened in the past, it has a potential to happen in the future if we can understand what controls it. Rates and sizes, time and space, hot and cold kind of cycles. A really good book that talks about climate change, I'd really recommend it to you. It's this book by Bill Ruderman called Plows, Plagues, and Petroleum. And he put kind of an outrageous hypothesis out there that coming out of the last glacial maximum up towards today, right? Clearly, by seeing that heartbeat kind of pattern of climate change, we should have been headed down to the next glaciation. And indeed we were. But we kind of stepped off because of flooding rice paddies, cutting down forests in Europe. We started to venture across and flatten out this curve in the last 5,000 years or so. We should have been crossing and starting to grow the next ice sheets, but we suspended that by our human activity. And that's different from what we're seeing today, which is this really rapid rise in temperature and in CO2 up through that. But if we look at this curve and this long flat line here, and we think about our human civilization, we can see the pattern of interglacial, glacial, interglacial, last glacial, and then this long period of stability in our climate, which has led to the development of our civilization. And then where we are with that kind of a pattern and what 2 degrees of warming might look like. The Paris Accord, the Paris Climate Accord, is trying to suspend things and keep things temperature at 1.5 degrees. By 2100, we are projected to go up here, and we don't want to go there, right? We want to reverse this problem. So just some general questions in here. Does it merit our attention? Is there urgency? Who's going to pay for this? Who should lead? Who's going to suffer the most? How are we going to manage that inequity? What if others don't change? Should we make those changes? Should nations be able to build their economy but using cheap energy like the U.S. and others have done, right? So a big part of this is really the impact and role of knowledge, which I'm happy to be talking to you guys as educators. Some questions that I think cause people to be in a defensive way is to think about the blame. Who's to blame for this? Who should pay for this? And I think that's the wrong perspective. I think we should be looking forward in this at solutions, working together. So this picture of the Nebraska sandhills here down, looking into the future, I think is a good way to look at this. Of course, these concepts are pretty important for all of us, I think. Sustainability, stewardship, science literacy, steps we can take by gardening, by drying our clothes on a line, by walking more than driving. All these different things can play a role, right? And we can all play a role in this, individuals, but also on longer scale parts of our economies, political systems, economists that are getting together to shift the way that we engage with the environment. But why do this? It's because this is our planet. There is no planet B. There is no other place to go. And we should clean up our act here so we can live in it here. When we think about this, maybe in terms of family, and think about youth in this, I think it becomes a bit closer to home. When I talk about family here, I'm kind of thinking about not just humans in our immediate family, but also the other co-inhabitants of planet Earth, right? While our populations are growing, they are decreasing. The diversity of the planet is decreasing. If we think about our family, we can look at our history.
About 5 more minutes left.
Yep, great. That's great. Thank you. We can think about our family of other hominids in here, other smart creatures, sapient beings through here. And one thing I like to do with my class at this time, which kind of shocks them, is I will go and get a roll of toilet paper, and I will get a roll of, not promoting it, but Scott toilet paper that has 1,000 sheets. And the value of that is 1,000 sheets. We can deal with decimal places here pretty easily, of 3 decimal places with 1,000. And I actually run around the room and I TP the room by spreading toilet paper all around, because if I take the analogy that the length of the toilet paper roll represents all of the Earth's history, 4.6 billion years, and I tear off 1 sheet of toilet paper, 1 sheet, if you move 3 decimal places, of toilet paper represents 4.5 million years, rather than the 4.6 billion years of the whole roll. It's 4.5 million years. And then I start to fold this roll. I fold it in half, right? And we get to, 2.5 million, fold it again. We get to 1.25, fold it again. We get to like 600,000, fold it again. We get to, 300,000 or so. And we get to basically the record that we could potentially see in the ice core record. If you fold it as far as you can get, and as far as you can fold it, you get to basically where our modern civilization comes in, right? And of course, I've got this length of toilet paper all around the room, but it shows how limited, how narrow is our time frame on, and how long we've been here, but we've made such an impact on the planet to this point. So just a little bit in summary of some of the things that we've talked about. There is this natural variability of climate that we've seen based on carbon dioxide. Going from 180 to 280, we see the growth and retreat of the Antarctic ice sheet. We see the growth and retreat of the Northern Hemisphere ice sheets. And we've seen it on this pattern of change. And down here, I have the numbers of folds, right? Basically for that toilet paper roll to keep that in some perspective. Work we've done in Antarctica has shown that if we reach the level we are now at 414 parts per million or so of carbon dioxide, that the West Antarctic ice sheet is going to be gone. It's not going to happen instantaneously, but when things play out, when things reach equilibrium, this ice sheet will be gone at the level we have reached already. If we reach 750 parts per million, maybe 2150 or so, we reach across the threshold when all of the ice in the poles will eventually melt. And we will see that sea level rise of about 600 or 60 meters or so. That pattern of change, now that I got your attention with that bottle of whiskey, that pattern of change from these different levels of carbon dioxide, 200, 300, 400, 500, may not seem like a lot. And I hear some people say, you're talking about, changes in parts per million, 100 parts per million. It's not so important. How can that impact the planet in a big way? But these are the same numbers, right? 400 parts per million, 800 parts per million, 1,000 parts per million. It's the same as blood alcohol limits. You're just changing decimal points, but it's the same number. And clearly, right, to go from 0.04 to 0.08 blood alcohol limit, you're inebriated. You go to 0.1, right? You're probably not able to stand or walk very, very clearly. So I think that small amounts of changes can make big impacts. And just another alcohol reference in here, which I don't always give to my students, but the pacing of this is also important too. The rate of change is important. Mother Nature has enzymes in her natural systems that also can manage and keep things in pace, just like our liver, can control how quickly we assimilate oxygen in that way. If you drink a 12-pack in 12 hours, you're okay. Do it in 1 hour, right? You're going to be horizontal, So Mother Nature can pace herself as well. I really like this quote from Charlotte's Web. It's just that we think we're so smart, but we should learn a lot from Mother Nature, and work within her sustainable realm. My bottom line about this is chiefly this: there's nothing to believe about climate change. We know a lot. It's based on empirical information that we've obtained, and we understand how the Earth system works. It's not about belief at all in this way. So it really does come down to the things that we can do in this, and we need to avoid this future in terms of cold and hot. Communication and education is the key, and the work that you guys do is so very important. So that just concludes my presentation here. I'd be happy to answer any questions you might have, and I hope that you'll be able to take away something from this presentation that you might be able to use. I'd be happy to share this presentation with any of you if you would like. So
thank you.
Thanks very much.
Harwood, thank you so much. You're right on time. Well timed there. Very good. Thank you. We do have a few questions in the chat, so let's get over to those. Jason asked, as he improves his ability to share climate change with audiences, the one thing that he hears a lot, or a question that he hears is it too late, or this is too big? So what any suggestions do you have for him to what he can do to help? What can he do that really helps or has an impact? Any advice on that, dealing with the it's too late or too big of a problem?
Yeah, it's a really important question to how to still stay optimistic, how to keep hope with all this. And I've just seen in the last 10 years, last 5 years, so much more awareness of this situation, right? So that's the first thing, from awareness to then taking some actions. And people want to know more. You know, in my Antarctic class, I asked them, do you want me to convince you that this is happening? Because I used to do that, you know, when I started this class, and they say, no, just give us the information that you have so that we can also be communicative and active on this. It's going to take energy to solve this thing. It's been in terms of pulling carbon dioxide out of the atmosphere. It's doable, it's possible. There are a lot of good strategies for making some of these changes coming online, but we need an alternate fuel source, right, to be able to do that. So we need to change a lot. We need to stop what we're doing, shift to different sources of energy, and build infrastructure that's going to start pulling carbon dioxide out of the atmosphere. Some things may be permanent, some things may not be able to you know, to shift. Like, we're probably going to lose the Arctic pack ice. We're probably going to lose that. It's not going to come back. Once sunlight is warming that open ocean, we're not going to be able to, you know, to put it back, if you will. So there are going to be some changes that are long-term, but I think, yeah, optimism is there. Awareness, knowledge to action is really important. So the role you guys do is really important.
Thank you. And one more quick question here, similar, but asking about what to do to balance the doom and gloom of these kinds of topics, especially when talking with young children. So you kind of talked about keeping the hope alive, but do you have any maybe success stories or things that you've heard of that have worked that places are doing that could be shared?
I do, yeah, two things. Well, when that question also comes up, I just challenge all these young people to make a difference. You know, just say, this is the biggest challenge you're going to be facing. Whatever you do in your career, make it related to this. Invest something in this. You know, if you're just going to be a doctor and you're not going to impact climate change directly, you're going to have money, you're going to have resources, you can invest it in that. If you're going to be a poet, go ahead, write about this. You want to be an engineer in science, find a way to fix this. An economist, find a way to fix this. But engage, do this, make this a challenge for your generation. But some success stories, right? You know, we have unleaded gasoline, and we have that because we were poisoning ourselves by putting lead in our gasoline, and we reversed that, right? We also reversed the fact that we were using hairspray and deodorant and aerosol cans, and our air conditioning system as well. That was polluting the atmosphere. That was destroying the ozone hole, right? And we changed our practice with that as well. It costs a little bit, but it's for the better of the planet. So those are two examples, I think, of how we changed what we do. Our technology took that together. So it's going to be some aspects of change, I think, that are needed. You know, people back in, I don't know, turn of the century, last century, were worried about what are they going to do with all of the horse shit that was around in New York City, right? And then the internal combustion engine fixed that, right? So how do you get that stuff out of New York City? Didn't become a problem because we shifted to another technology. That's where we are, I think, right now. We need a transformational step to make these changes. So I can't hear you there, Jamie.
Thank you. I was just thanking you and saying that you're getting lots of thanks and appreciation for your presentation. So everybody, it looks like they've enjoyed that. Amber has linked a few things in the chat there. So if you're looking for, I think she linked a copy of the book that you had mentioned, and a couple other things. And also, if you scroll to the top of your chat, everyone, the Jamboard is linked up there, and I can see if I can get it in there again. And that way, if you have some additional questions, oh, Amber just did, thank you.